So, we know that in this kind of upscaling, in fluid mechanics, the motion of fluid particles is governed by partial differential equations. So these are the standard equations, Navier-Stokes equation for incompressible fluid. So that is one type. There are many other types that are there, depending upon the situation. So if you consider a porous medium, as we have been seeing in last 3.5 days, consists of particles, fibers, or any other kind of thing. It has a lot of pores in that. And so it has a very complex pore space geometry. Now, some people who are not used to the porous media idea, they might say, okay, why don't we just do a CFT model? CFT is ubiquitous. You have so many commercial packages, Fluent, Star CCM, and COMSOL, and so on. Why don't we just do that? Okay, and anyone who is little familiar with that porous medium will know that it's impossible to do CFT analysis on pore scale flow and transport for any reasonable size porous medium. You can do it for very, very small with probably 100 particles, 1,000 particles at the most. But beyond that, it becomes very difficult. For one thing, the geometry is very complex, very, very complex, and so it's difficult to create the mesh for that. And anyone who is doing CFT knows that mesh creation takes the majority of the time, 80 to 90% of the time. So it's impossible to do that if you have any kind of a reasonable size pore scale geometry. And as I said, the actual porous media may have billions of pores. Okay, so industrial scale porous media, they are smaller generally, but if you go to like oil fields or groundwater flow type of problems, you have miles and miles of porous media. So probably very, very large number of those pores. So you cannot do any kind of CFD at this micro scale. So I'm defining micro scale corresponding to that. Some people use the term mesoscale, but here I'm just mentioning the scale of the particles. And so today we are going to learn a little bit about the volume averaging method, where we can upscale from this micro scale to the macro scale. So just like we did earlier for fluid mechanics, we can describe the motion at the macro scale using streamlines, Darcy velocity vectors, and so on and so forth. So in micro scale, we do the flow modeling using the Navier-Stokes equation, whereas at the macro scale, after we are done with the upscaling, we do the flow modeling using Darcy's law, Brinkman equation. For transport, at the micro scale, we use the convection diffusion equation, standard ones. And then for macro scale, we just use the same type of equations, but the coefficients, you will see that it changes. It's no longer the coefficients that are used for these types of equations. So what is the basic concept? Basic concept for volume averaging is the idea of representative elementary volume. Okay, so you basically have to average the flow variables in this domain, the REV. Okay, and here is a schematic. So you have this two different phases. Here I'm just referring to a single phase flow through porous medium. Okay. There may be multi-phase flow porous media, but first we have to understand the single phase before we go to the multi-phase, because that is easier to do this way. So here we have the solid phase, and you also have the fluid phase. By the way, if you have any questions, please raise your hand and ask. Okay, feel free to interrupt me and as we go along. And so I'm setting up some definitions here. So let Q subscript F represents the fluid phase, be any flow quantity. So it can be pressure, it can be velocity, it can be temperature or solute concentration or so on. And so let's now come to what are the basic averages that are used in volume averaging theory. So the first one is the phase average, which is also known as the volume average or superficial average. So this is just an integration of this flow quantity in this REV. So you have this VF. VF is the volume of the fluid phase, okay, which is also the volume of the pore region within the control, within the REV, okay, because we are assuming that all the fluid phase is connected, is occupied by one single fluid at this stage. So, so you integrate that over this fluid volume, and then you divide by the capital V, which is the volume of the REV. Okay, so that's how you get the superficial or the phase average like this, and these are the description. And if you have those, laptop, or you can, keep track of these things. The other important average is the intrinsic phase average, which is also known as the pore average. So it's kind of similar. It's an integration of that quantity over VF, the fluid volume within the REV, and then, but instead of dividing by the total volume of the REV, we are going to divide by the fluid volume only. Okay, so and then we have additional subscript on top. So just to distinguish between the previous one, which was the, so earlier there was no additional superscript on top, but now we have that. Okay. So an example of this is the average pressure as measured in a porous medium. Okay, intrinsic phase average. We take that because people have found over the years that that pressure is closer to the pressure that is measured by the transducers or any other measuring devices for the pressure. Then we come to porosity, which is defined, in this case will be defined as the fluid volume divided by the total REV volume. Okay. So that is epsilon F. F is the subscript for fluid. And note that total volume is the fluid volume plus the solid phase volume. And so similarly we can define epsilon S, which is the solid volume fraction. So that is the volume of solid divided by the total volume. So and you can see from this relation, we can, these two definitions, we can say epsilon F porosity plus solid volume fraction is equal to 1. Okay. Okay, now what is the relationship between these averages, which is important to see. So I'm going to start with this relation B, which is here. So this is your intrinsic phase average, and so this is the definition. And what I'm going to do is, now I'm going to divide by V, and then I'm going to multiply with V. So that way V gets cancelled, and you get the original thing. So, and as you can see, VF by V, that is your epsilon F, it's the porosity. So, and then this, what do you think this is? Feel free to answer also. Yeah, it is the superficial average. Okay. So, so that is the intrinsic phase average, and this is the superficial phase average, or just the phase average. That is divided by the porosity. So this is the relationship between them, or you can you state it like this. And in the volume averaging theory, there is generally length scale constraints are important. So, for example, the LF, the length scale of the channels between particles, okay, interstitial spaces between the particles, is generally much smaller than the REV size. Okay, it is that's what it has to be. Unless you decide to average and along certain direction and create it for a thin porous medium, so that is another matter. But for any general upscaling problem, the particle channels, interparticle channels or particle themselves, they should be much smaller than the REV size. So size of REV is much bigger than the individual particles, and REV size in terms of the total domain should be much smaller. So that is the another relationship. So that is the length scale for the REV. Characteristic length of the REV should be much smaller than the domain length. Okay, so I hope that is kind of familiar to most of you. Yeah.
Do you have next to a constraint for length scale separation also a constraint for time scale separation?
I think there are constraints like that. So I'm not going to go into the those kinds of constraints. Would you like to comment? Time scale
for the I will actually the purpose of my presentation at the end of this course is about non-equilibrium systems for which there are some time scales which are very, very important. So each time you are doing some averaging, there is an interplay between time scale and spatial constraints, and we will see some examples at the end of the course. But you're right, they are.
Yeah, so generally,
there are also process constraints. This is a geometrical view, but of course, what is important are gradients of the physical variables. So if they are small or big, so they are not only geometrical characteristic length of time. There are time scales which are related to process, and there are also length scales which are related to process. Which you are interested in.
So anyway, we will see the example when Professor Quintard takes over. So this is, I'm just keeping very, very simple description. So the REV size should be much bigger than the individual particle size, but it should be much smaller than the domain size. So that is the general well-known conventional wisdom. And by the way, I would like to say that if you want to pursue the volume averaging seriously, I think this is a good book to have. Professor Whittaker, the method of volume averaging. So as you can see, there are so many, I use it quite often. So all the length scale at the initial level, a lot of description is there in this book. So what if you, how do you find out if your REV size is correct or not? Okay, especially when you have like some kind of a scan, SEM or micro CT scan, and then you want to average and you want to upscale. So what should be the size of your REV? So this is a kind of modified picture which actually I took from Jacob Baer, but many people have used it in their books. So if you take that this is like those averages, a phase average, intrinsic phase average, and then this is the size of the REV divided by the interpore space, the interparticle space distance. And so if your REV size is very small, you will see that the particles can be of the same size as the REV, and if you increase the size a little bit, there's a big change in the averaged quantities. Okay, so initially if you start, there's just one particle is there. As you increase, now there is a fluid phase around that, and then you include another particle. So if your REV is very small, you will see a lot of fluctuations in these averaged quantities. But as it becomes bigger and bigger, you will see that it reaches some kind of a steady description. So the fluctuation region, I will call it a domain of microscopic effects. And when you reach some kind of a steady description, it is the domain of macroscopic description. And if you keep on going further, and if it's a very large domain, like an oil field or things like that, other inhomogeneities present, so you will start deviating from this straight line for the homogeneous medium. So in general, the REV size should be such that the effect of adding or subtracting one or several pore particles has insignificant influence on the value of an averaged quantity. Okay? A general rule of thumb. Similarly, REV size should be such that the translating it around. So let's say you have a micrograph, you choose a certain region as your REV, and if you translate it little bit, there should not be any much change in the value. Okay? So translating it around should not change the value of the averaged quantities. Okay? So there's a general rule of thumb that we can have. I think I'm done with this part. So this is like a brief introduction to the volume averaging
I just
concept.
have a question related to that.
Yeah.
Some people use in the literature, the Brinkman screening length. Can you comment on this? Are you familiar with this
Brinkman screening length.
screening length? It's a paper of Clark and Phillips, I guess.
There are many that's related to discussion. Yeah, there are some process-dependent times and length scales. And so, for a specific process, you may want to introduce a specific length scale. This discussion is rather generic. It's based on a geometrical view, as I said before, but it's not the end of the story. So we have to each problem. I will try to forward that message in the second part of the lecture. Each problem has specific considerations to take into account. So that's one example, but there are many other examples.
Any other question?
No, I think the Brinkman term occurs when you have wall effects, and it can also be seen as kind of an homogeneity problem.
Yes. So I will be talking about that, how it appears when you volume upscale from the Stokes equation to the higher level. Those Brinkman terms come, and usually they are small for a homogeneous medium, only close to a channel, flowing channel, a liquid channel, and then it becomes important. Otherwise, they're not. Okay, so this is the first part, the introduction. Let me go to part 2, which is a little bit about the tensor algebra. Because if you want to seriously pursue literature in volume averaging, it's my faith that you should know all these kinds of manipulation quite well, at least the type that I'm going to show. And much of it is, I've taken it from one of the appendices of this book by Whittaker. So I would strongly advise if you want to seriously pursue, you can get. Of course, I'm giving much more detail than what is there in the short appendix, but the idea is basically the same. So generally, it is nice if we can have index notation when we are dealing with vectors or tensors. And usually in volume averaging literature, we generally deal with vectors and second order tensors. We generally don't go to the higher order tensors. Unless we are dealing with multi-component fluids and other things.
Also,
Yeah, solid mechanics, if you constitutive relation between stress and strain. So let's say you have a vector, and these are the three components: ax, ay, az. And as we know, these are the orthogonal unit-based vectors. And these are the components of the. So we can equivalently we can say like this. So instead of saying I, j, k, we can say E1, E2, E3, which are the unit vectors along the three basic coordinate directions in Cartesian coordinates. And we can sum them up nicely like this one. Okay, so is everyone familiar with that one? So it's just adding these things, and if we follow Einstein's summation convention, that is, if the two indices are getting repeated, then it is understood that it is a summation. So that way we can get rid of this cumbersome summation term also. So it's a nutshell the summation convention. Repeated indices are summed from 1 to 3. Okay, so, but you have to be careful. If you are writing in terms of I, J, K, you have to make sure that, say, I, for example, it should not come 3 times or 4 times or something like that. So it should just come 2. Then only it means summation. If it is 3 times it is coming, it's a mistake. Okay, you are not following the convention correctly. So it's a bit of an art to handle this thing. But I generally found that it's easier to work if you mastered it and understood it, it's fine. So let's take an example. Let's say a dot product between 2 vectors A and B. We all know it's magnitude of A times magnitude of B and the cosine of the angle between them. So that is A dot B for you. But you can also represent A dot B in the form like this. So you take the whole description of A and the description of B, and then you take the